The TCGS framework, which stands for Timeless Counter Space and Shadow Gravity Sequention, proposes a strict singularity identity postulate. It states that all observable matter and phenomena originate from a single mathematically pure point in a higher dimension. This fundamental origin is known as the territory. It is a four-dimensional, timeless counter space that is ontologically simple and completely unified. But when we measure the physical universe across different scientific disciplines, we do not see that perfect unity. We record a multifractal universe where structures exhibit infinite scaling variations and broad spectra of exponents rather than a single mathematical rule. How can a framework asserting exactly one fundamental singularity at its origin produce the vast spectrum of complex, scale-dependent mathematics we measure in nature? Resolving this paradox requires an epistemological shift. We have to stop confusing the fundamental physical reality, the territory, with the distortions created by our restricted three-dimensional perspective, which is the map. This animated diagram shows how information from the timeless four-dimensional counterspace projects down into our observable three-dimensional manifold. That three-dimensional shadow is where multifractal scaling actually occurs. It is driven entirely by the geometry of the projection itself, without requiring us to invent new types of fundamental particles. The act of projecting a higher dimensional object onto a lower dimensional plane inherently fractures a single unified rule into a continuous spectrum of local scaling behaviors. This introduces descriptive incommensurability, the mathematical principle that a complete four-dimensional reality cannot be perfectly compressed into a three-dimensional representation. Our mapping will always appear infinitely complex. Discovering multiple scaling exponents in nature does not mean we are finding new fundamental particles. It means we are successfully mapping the geometric distortions of our own three-dimensional existence. This chart shows the three categories of mathematical scaling. On the left is exact scale invariance. In the middle is asymptotic scaling. On the right is multifractal scaling. The first category, exact scale invariance, is a theoretical ideal. It almost never appears in actual empirical data. In the TCGS framework, our three-dimensional world lacks perfect scale invariance because it is bound by embedding constraints. These are hard geometric limits placed on the projection from the higher dimensional source. We observe these constraints as absolute boundaries in physics. The Schwarzschild radius defines the strict limit for gravitational mass, while the Counte wavelength defines the absolute boundary at the quantum scale. The breaks, crossovers, and limits in empirical scaling data are not random noise. They mark the exact boundaries where our three-dimensional reality physically collides with its four-dimensional geometric limits. Four specific physical mechanisms mathematically distort the single origin into a multifractal shadow. The first is Jacobian weighting. As the projection map drapes across the three-dimensional manifold, it stretches and compresses unevenly. The second is the pullback structure. When a uniform field from the four-dimensional source is pulled down into three-dimensional space, it loses its uniform intensity. The third mechanism is interference. Information from different regions of the fundamental orbit overlaps in the shadow. These overlapping nodes, known mathematically as off-diagonal terms, act as the primary drivers of scale-dependent variation. Finally, the constitutive law cascade regulates the tipping point. It determines whether a system remains stable under single-source dominance or fractures into chaotic multi-source interference. Together, these four geometric mechanisms act as a natural prism. They fracture one fundamental physical identity into a wide spectrum of measurable phenomena. MFDFA is the primary mathematical toolkit used to isolate these signals. It segments a highly volatile time series into discrete vertical windows to find local trend lines. By analyzing the variance within these segments, we map them to a single mass exponent. Next, a Legendre transform converts this mass exponent into the definitive singularity spectrum, appearing as a concave downward-facing curve. The horizontal axis measures the local Holder exponent, representing scaling strength. The vertical axis measures fractal dimension, indicating how often that behavior occurs. This unique concave curve is the definitive fingerprint. Researchers use it to test whether a measured observable is a fundamental physical constraint from the territory or just a statistical illusion. To isolate physical invariance in the real world, we apply the MFDFA toolkit to geological records. The Chicxulub asteroid impact serves as a massive, sharp singular event used to anchor multifractal geological time. We ground this macro event in microscopic data. Researchers hunt for isotopic signatures strictly within the KPG boundary, the specific dark rock layer deposited directly by the impact. Analyzing magnesium, iron, and calcium isotopes within this layer reveals highly nonlinear, multifractal scaling behavior. Geophysicists used a width of this multifractal spectrum to separate the data. A stable, wide spectrum isolates true impact material from secondary environmental noise. Geology provides a billion-year baseline, proving that extreme singular events leave permanent, scale-dependent constraints embedded in the Earth's crust. This diagram plots a multifractal spectrum from telenology, the study of fossilized pollen sequences. Notice the axes. Palynologists face a persistent scientific problem, aligning physical depth with modeled age. This introduces the chart stability criterion. Watch how the spectrum curve remains entirely rigid and stable, even as the underlying measurement axis stretches and compresses. If a scaling feature survives this transformation between depth and time, it represents a true, fundamental geometric constraint. Conversely, if the spectrum breaks apart when the chart changes, the observed scaling was merely a foliation artifact, a mathematical distortion caused by the mapmaker, not the universe. Time itself acts merely as a gauge. True physical reality persists and holds its shape, regardless of how humans choose to parameterize the timeline. We can scale this analysis up to the cosmos. Deep space catalogs map the large-scale structure of the universe using precise observational data. Astrophysicists analyze galactic Counte cells and established scaling relations under MFDFA, testing them across different models of cosmic redshift. When we compare the resulting multifractal singularity spectra from geology, palynology, and cosmology, they overlay perfectly. Despite having different numerical values on the axes, they share the exact same concave shape. This exact visual alignment is known as template universality. It is the quantitative proof that these disparate phenomena share a common origin. The universe is not an assembly of endless disconnected fundamental particles. It is a single, timeless identity. When its mathematics project into three-dimensional space, it shatters into a universal, measurable, multifractal spectrum.